Okay, so let's fix x, n, and beta. So we have our moduli space. Here, this is the direct sum of the cohomology groups. So takes n elements in this direct sum, so they can be of different coordination. And we impose this, that the sum of the coordination of each one is equal to the dimension of the moduli space. Then a Gromov-Witten invariant is this number that basically is the degree of this. What does it mean geometrically? So imagine that we have our x, and we have these cycles. So this supposes gamma 1, this is gamma 2. Okay. So AB star gamma 1, AB1 star gamma 1. What does it mean? It is basically, okay, it's the pullback of these cycles. Geometrically, even if this is just a geometric intuition, it's not formally true, but let's think in more relaxed terms. This is the cycles of all maps such that the first market is image containing in gamma 1. So imagine we have a map. This is C. This is 1. This is 2. So the image of C here in this intersection means that the first market point is over gamma 1. The second market point is over gamma 2. And so on. So this condition implies that this is a zero cycle. Oh, yes, a zero cycle in the sense that its codimension is equal to the dimension of this. So it makes sense to take the degree, and this is a number. In general, it's a rational number because this is orbifold. So in order to have an intersection theory, we have to enlarge to rational number. And what more can if this condition is not true, then this expression is by definition zero. Okay, this is the Gromov-Witten invariant, and a quick remark. I will write here remark. Morally, M0 and X beta. Okay, this one, AV1 star gamma, AV star gamma. Count the number of maps C, P1, Pn, mu, such that mu P1 is in mu Pi is in gamma I for each I. Okay, this is just a very not rigorous remark, but since I suppose it's the first time you see this stuff, this is a good way to start how to think of this number. Morally, they count that. and there are cases where this is true, and there are cases where this is not true for some reason. Okay, let's see the main property of these numbers. Okay. Okay, pro. Okay, the integral, I mean, with the integral with the Gromov-Witten invariant. The integral is invariant by permutation of gamma. Sure. If beta is 0, clearly n must be at least true, at least 3. So this is implied by this. Then the value of this integral m0 n x0 AV star 1 gamma 1 AV star n gamma n is equal to gamma 1, gamma 2, gamma 3. Okay. If n equal to 3 and 0 otherwise. I mean, I can leave this as an exercise very easy. Prove it using just to let you to understand better this stuff. And 0, 0, 0, x. And projection for. Okay. 3. If gamma 1 is equal to x, I mean, and when I say gamma 1, I mean any of them, because the integral is invariant by permutation. So I can suppose that is the first one. Okay. This one, don't let me to rewrite again. This stuff. So I leave you to time to write. Is equal to gamma 2, gamma 3, if beta equal to 0 and n equals to 3 and 0 if n or beta is okay. Again,
E é menor que 0 ou menor que 3? Embaixo. Embaixo.
n é maior
0?
maior que 6.
Não é 3?
No, it's not 3. It's not 3 because beta can be not 0. Okay, sorry. It's not exactly the same. It's the same. Here, I don't suppose any. Here, I don't suppose beta equal to 0. So it is not the same of this. This is beta. It could be not 0. So the value of this integral when gamma 1 is x is more or less like this when beta is equal to 0 and n equal to 3. So we are in this case. Or 0 if n is greater than 0 or beta is different from 0. I mean, if beta is different to 0, this is automatically 0. And if, yeah, let's. Let's otherwise. Otherwise, so it's easier. So when this condition is not it doesn't is not true, then it's always okay. Again, exercise. Prove it. Okay, using to and forgetful map. The forgetful map is the third point in the recap. So it's the map that forgets the last point. And finally, last. Can I write here? Thank you. Or if gamma 1 is a divisor. So it's a codimension 1 cycles in the complex sense, and beta is different from 0. Then M0 then it's beta. Everyone okay. So it's gamma 1 is a divisor. I can put it outside the integral and it becomes this. This is some quite logic. Why? Let's go back to the geometric intuition. So this is x. This is gamma 1. This is the same draw that there was here before. Okay, this is a divisor, and the image of C is a curve of degree beta. So it means gamma 1. This is the image of C. it means gamma 1 exactly in this number of points. So, if I have C with its first map, this first map has this number of possibility to have its image. So, I can remove gamma 1 from the equation and multiply from this number, and it's the same. Because consider that since this is a Q, the image of every curve will meet gamma 1 in some sense. More or less. Not completely true, but the geometric intuition is very helpful. Imagine that gamma 1 and beta meets no, gamma 1 and C meet in this number of points. So the possibility to the image of these points are exactly equal to this number. So you have this number of combination and so on. Okay. All right, these are the definition of, and the main property of Gromov-Witten invariants. Now we enter in quantum cohomology. So if there are no questions, I change to the new topic. I'm in here. Okay. Quantum cohomology. Okay, let's fix notation. Okay, no, let's, before to start, what we are going to do here now. Okay, idea. Okay. We have a ring structure of X star XP. Actually, it's so X is our smooth variety, and we know that we have a ring structure here. But I missed the dimension of X. Okay. I just don't want to. Okay. No, don't make confusing with the notation. This is just the tensor of this wish 2. So M is the dimension of this as a Q vector space. Okay. So we have this. Okay, so we have this ring. So we have a basis, and we can consider this other model, this other ring. Then we have a natural operation, a natural ring structure on what? H star of X tensor with 2 and 1 A. It's simply so. You know what is this? This is a polynomial in n variable with an infinite degree. So we don't ask if converge or not. It's just formal polynomial. Okay, so we have okay. There is a natural ring structure that is just the product of the two ring structure. So alpha. Well, this is the operation of this ring, and this is the just the multiplication. Okay, the quantum cohomology is give us a new ring structure, a different ring, giving us a different ring structure on. So what we are going to do is to tensor this space with this space. This comes with a natural operation, but we will consider the same space with another operation. And to do that, we will use the Gromov-Witten invariants. Okay. So now I can go back to what I was saying before. Okay. So we have an homogeneous variety. In a homogeneous variety, the cohomology is the best possible. I mean, we have a basis. We have the basis also simplicial in the sense that there is a basis where each effective class is a positive combination of the basis, of the element of the basis. Okay. With n from index from 1 to n, we mean all the bases of h star of x, and up to p, we mean the basis of all of the codimension 1 cycles. Then we have the intersection. Maybe before I use the symbol point, but I think this will not make confusion. You can use also this notation. Okay, so yeah, this makes sense. This is not zero by definition when codimension of pi plus codimension of dj is equal to the dimension of n of x. So we take the classes from 1 to n and we intersect each other and we construct a matrix. And we we denote this matrix with these symbols. So this is the matrix of all intersections, and this is the inverse, and this is the diagonal of x times x. Okay, just to be practical, h star of the projective space is what? Is zeta with one variable which generates everything. Okay, T is a generator of H2 PS zeta. And all other classes are just power of T up to S, because T intersected T to the power of S plus 1 is 0. So in this case, is 1 T square Okay, so T the power of I. So Ti on Tj is 0 when these are not of complementary codimension, and 1 when they are of complementary codimension. So in this case, this matrix is 1. And 0 to x. So this is the most simple case. Okay, why? Because okay, here we have 1, and here we have Ts. Here we have Ts minus 1. Here we have 1. So we make 1 to 1. They are not of complementary codimension, so it's 0. 1 with T, they are not of complementary codimension, and it is 0. And so on. And G Ij as exponent is the inverse of this matrix. Okay. Okay. I will give you time to write. If you are. And when we consider homogeneous space more in general, the intersection theory is very easy. We have it's not very far from this. I mean, we have this space that is bigger. But the matrix is very easy to compute. Okay, this is an important remark. If X is homogeneous, we can find a basis such that for each I there exists a unique index J, let's call it Ji, which depends on I, such that Ti meeting Tj is 0 if J is different from Ji, and 1 if J equal to Ji. So when we have a homogeneous, this matrix is full of 0 and 1, and for each row we have exactly one coefficient that is 1. So this happens in homogeneous case. So this we have more or less this matrix. So for this I mean that the intersection theory in homogeneous case in homogeneous varieties so easy. This is an important level. Okay.
The homogeneous case is always a reductive variety divided by a parabolic group.
A complexly group.
Complex reductive, I think, maybe not necessarily. A complex algebraic group divided by quotient by a parabolic. Yes. Yeah, let's do
Complex. We also consider the C case.
Yeah, sure. And,
so it's a reductive.
Yeah, and P is a parabolic.
T. Parabolic. Okay, this is a definition of homogeneous, which from the fifth lecture I recall you include the projective space, Grassmannian, etc. SG, and G, or G, and other flags. Okay. Okay, this is an important lemma with pretty long proof. So let's be ready to a long proof. Lemma. Let n be fixed. Gamma in H star of X. That's that. Okay, so what we are doing here is we consider this Gromov-Witten invariant where n is fixed and then gamma is fixed for each n. And what is variable is beta. And what we are saying is that when X is homogeneous, we have finitely many class beta such that this is different from zero. Okay, so this is what we are going to prove. Okay, let a rational curve with plus and because mu constant means beta equal to 0. And then mu p p1 mu star p x is not, and if mu is not 0, this cannot be 0. It is a general fact that every vector bundle on P1 like mu star the pullback of the tangent space of X is isomorphic to a direct sum P1 and this is called Grothendieck theorem in the literature. Since zeta 0 is different from d mu, and d mu is a map from the tangent space of P1 to the pullback of the tangent space of X, because this implies that 0 is different from this space. So this space is not 0, but we know who is this. This is O P1 of 2. And this is this space. So the tangent space is O2, and this we know that is equal to some direct sum of O P1 lambda. Okay. Ohm commutes with direct sum. Op1 2, Op1 lambda. This is a general property of the Ohm function. So this is equal to O P1 lambda I minus 2. And this is a Ohm from O to this line bundle is canonically isomorphic to H0. So this direct sum is different from 0. And this happens if only if at least one of this shift is not with negative degree. So it exceeds I such that lambda I is at least 2. It can be 2. No problem. Okay, it can be 2. In this case, we have H0, 0, that it's C, and it's not 0. Or it can be greater, but at least one I mean, not exactly one, at least one, can be more than one. Must be great attention. Okay. Okay, we didn't use that X is an homogeneous space still. We just use the fact that is moved. Because if this move, this is a vector space, the pullback is a vector space. So it's a vector space on P1. So we just use it that X is moved. Let's use that is homogeneous space. More exactly, that is convex. By convexity of X, every composition where F is any map, non-constant map, is such that H1, okay, the definition of convexity is that for each map from P1 to X, the pullback of the tangent space has 0 H1. So in this case, it means that this space star of space 0. Okay. If n is that is not the same. If F is n cover, in my notes I wrote n, but it's not the same n of this n. So I'm going to use another. So then H1 of P1 and alpha I equal to 0 for each alpha. Okay, what I'm doing here, I just instead of consider mu, consider the composition F times mu. We can do the same stuff of here. So what happens if mu star of the tangent of space of X is this one? If I compose with F, what I got is that this is multiplied by n. So the effect of F is just to multiply by n, because F is the m cover. You get this just by repeating this argument with F composed to mu instead of just mu. So this is X0 P1 HP1 of minus 2 minus m alpha. This must be 0. Okay. Okay, so this is 0. This is equal to this, and must be 0. This is true when this is strictly less than 0. This number here, strictly less than 0. This is equivalent to say that m times alpha I is greater to minus 2 for each n. Now, if alpha is minus 1, I can choose the fact that m alpha I is greater than minus 2 for each n implies that alpha I is greater than 0. Because if alpha is negative, I can multiply for a big n in such a way this is not true anymore. It's clear or not? So the fact that this is true for each m positive means that alpha I must be at least. Okay, so we proved that there exists an I such that alpha I is at least 2, and alpha I is at least 0 for each I. So this one, we proved this one and this one. Follows. This is by projection formula. Projection formula. Okay, so these two facts implies this that this degree of this cohomology. This means first chain class. Okay, this is basically -kx times b. Okay. I just use another notation. I did it to do speech before, but this is first chain class. So this is beta by construction of mu. This is by projection formula. This we suppose that is the direct sum of these spaces, and the first chain class is just the degree of this one. And the sum of this lambda I is at least 2 because we proved that all of them are non-negative and at least one is at least two. Okay. Let beta 1 be effective in classes plus okay. The number of the generator of H2 must be the same of the number of generator by H2 with the 2 up. This is by Poincare duality. Moreover, another fact here that we are using the homology class is that the generator of this it's the relation between the effective class inside the whole space. I mean, okay, I will say this before. That is, any effective one class is of X is a non-negative combination of beta 1, beta 2. Here, this is true because X is homogeneous. In general, okay, we have the generator of this space. They could be effective, but it's not true in general that an effective one cycle is a non-negative combination of this one. I mean, I can have effective cycles that are, for example, beta 1 minus beta 2. Okay. This doesn't happen when X is homogeneous. So the generators are effective, and every effective one cycles is a non-negative combination of this one. So this is only because X is this one. And if you take the blue up of the projective space, this is not true anymore. For example, in the projective space, we have a unique class that is the class of a line. And every effective one cycles is homologically equivalent to a multiple of this one of this cycle. Okay. Okay, why this is true? Okay, since this intersection is at least true, this is what we proved for every fixed beta. I mean, for x beta I, for every integer n, there are a finite number, n can be arbitrarily big. There are a finite number of beta effective cycles. So this is a non-negative integer, such that the intersection of kx with beta is at most n. Why? Okay, because then kx and beta is sum I then kx times beta I. Each one is at least true, so this is at least true. So if I impose that this sum is such that I continue to express such that such that is a variable. Menu kx times beta is at most n. So let's finish. Okay, let's remember that this Gromov-Witten invariant is 0 if this is not at 0 cycle. So if the sum of the codimension of the gamma I is not equal to the dimension of m bar. So if this is different from 0, implies this. In general, the other implication is false. I mean, I can have this, but at 0 Gromov-Witten invariant. But if the Gromov-Witten invariant, so it's well defined, this is the necessary condition. And this codimension, each one of these codimensions clearly is each one of these is at least the dimension of x, clearly. So what I have here is that this is equal to n times the dimension of x. So dimension of x plus number of integer. Yes. Okay. So we want that this Gromov-Witten invariant is different from 0. It is necessary that we have this inequality. Each codimension of gamma is at most the dimension of x. So the dimension of the moduli space is at most, because this is between from 1 to n. But it's we don't have gamma 1, gamma 2, gamma n. We have just gamma. So this is a sum of constant n. So this is at most the n dimension of x. So this is the dimension of the moduli space, which is at most we prove it that it's at most n times the dimension of x. So this part, which is the unit that depends on beta, is at most this one. So this implies this inequality. I choose this as my n, and so before there are a finite number of beta such that this inequality is true. And I prove it to you. Okay. Let's just give the last two definitions, if there are no questions. No question from internet? Now, so we have that this is a general rational number. Okay, if gamma is a if gamma is a cohomological cycle, this is a rational number, so this is sum of rational numbers. But what I want to do is to take gamma equal to sum of epsilon I pi, where I recall you, ti is the base of all the cohomology of X, and epsilon I are formal variable. This is just to point out that when gamma is written in this form, I mean a sum of a formal variable and ti, this becomes a formal polynomial. Why? Simply because by linearity I can use linearity of push forward and take the epsilon I out of the integral. So more explicitly,
Ali tens I beta de gama n. In the middle, tens aí I beta de gama n, não é? No fim.
okay. Okay, I'm using here a notation that I did introduce, sorry. Epsilon beta, gamma 1, gamma n, is the integral, the Gromov-Witten invariant, okay? And this gamma n, okay. So, when I have this here, I can use linearity on the sum, then linearity on the product, so this can be outside. And what I get is this one. So, this comes from this n factorial. And this is the polynomial in y. It's y. And where do we use the lemma? We use the lemma because when you say that this, okay, by lemma, the lemma we just proved, this is a finite sum. So, for each integer that sum to n, a positive integer that sum to n, So this sum is our n that is fixed. We know that there is a finite number of effective class beta such that this is not 0. So this is a sum where all except a finite number is 0. So this is a finite sum of non-zero rational number. This is the polynomial. This is just to take trace of what we are intersecting here. And this is called potential.
This one?
Potential. Gromov-Witten potential of X. So the Gromov-Witten potential is an element of his ring. That is one of the two rings that we use to define our Gromov-Witten, our quantum homology. So let's end with an important definition. Definition. The quantum. No. Oh, another definition, people. This is a polynomial, so we know very well how to perform derivative, and we denote here EJK, well, EJK an index. The derivative of this. Exercise, convince yourself that this is equal to this. Is exercise, but we don't need now this exercise. So we just need this derivative. The quantum product X maybe I used Q before, but it doesn't make any difference. Doesn't make any difference to put Q here. It's the same. Okay. So I have this space with a natural operation, but I'm going to use an alternative operation that is the following. Is linear with respect to this ring. So I need to define it just in the basis of this. So Ti times Tj is, by definition, in this new product, sum between L, F, E, J, L, G is the matrix we defined before, L, F. So this is enough to define this operation because, as I say, is Q linear, Q epsilon y epsilon n linear. So I just need the basis of this. And on the basis of this, the operation is defined like that, where this is the Gromov-Witten potential of X. Okay. It's obviously commutative because we know that the derivative commutes. So it's clearly commutative. As a very easy exercise, prove that the zero is clearly zero here. 0 dy times 0 is 0. But who is the neutral element with respect to this operation? The neutral element, I mean the element such that who is exactly the class of X. Okay. So something in common between the natural operation here and the star operation is that they have the same neutral element. Next time we will see that it's also associative, and this is the hard part. So if there are no questions, let's
Questions?
comments no. Okay.
So question, this reduces to the usual cup product for which phi? Constant one or
For which? Sorry.
so for which so this should reduce to the
No, this is not
not the deformation?
It's not a deformation of the productive. It's not a deformation. This,
okay. I see.
Deformation of the natural operation on here. It's not a deformation, so there is no continuous way to pass from one to another.